Alright. Real quick before I keep going, on Google Classroom, if you weren't here Monday, which I think we were all here, but if you weren't here Monday, or you are still totally lost about the math behind thermodynamics, there's a 29-minute video that's posted on Google Classroom for your viewing pleasure. If you have trouble going to sleep, you can watch this, or if you want to go back, and especially the practice that we do today, this will walk you through how to do it. So if you get lost, it's on there. And then before class on Friday, can you put the money up, please? With stats, there's a lot of key terms that go with it. There are over 30 of them. Instead of wasting class time with these key terms, before Friday, if you will please review this Quizlet. You may even have time today in class. I don't care how you review them. If you want to use them as flashcards, matching, I don't care. Just go through them because there are a lot. And if you're at least have seen and familiar with these words, it will help on. So. All right, let's go over 1.3. So number 18. We did this one in class on Monday, but I still want to review it. You have a kilogram piece of aluminum. Those 90 degrees Celsius is placed in 4 liters or 4 kilograms of water at 25 degrees Celsius. And we were determining final temperature. So my known values are on there. And then my unknown, I do not know the final temperature for aluminum or water. And remember, they're going to be the same because it's an equilibrium. So the equation is going to be that Q times M times C times temperature difference. And the Q for aluminum is the same for Q as water. Because the energy aluminum loses, energy is going to gain it. And so then I can set those two equal to each other. The mass of aluminum times heat capacity of aluminum times temperature difference for aluminum is equal to mass of water, heat capacity of water, temperature difference for water. And then you just start plugging. So my mass, my heat capacity, and then I don't know the final temperature, so I don't know my temperature difference. So my aluminum started at 90 minus final temperature, and that's all set equal to the mass of water, heat capacity of water, and then same thing with the water. I don't know final temperature, but I do know my water is going to get hotter, right? Because I'm putting a big old block of hot aluminum in there, it's going to get hotter. So that number is going to be bigger, so that's why it's TF minus 25. Because I know this number is going to be bigger. So then I simplify it a little bit more, then I'm going to distribute over. And that's what I end up getting there. I'm going to move that 900 over. And then I get it down to here, and then I'm going to move that 418,000 over. So I end up with 499.4 equals that 17,000. Divide by 17,000. My final temperature there is 28.3. Are we good on that one? Yeah. Cool. This box problem, to me, is probably the hardest that you will deal with for this unit. And I purposely leave it in here because I don't know what's gonna be on the EOC, so I don't know. And this is a PL2W problem, so I don't put it past them. So this is a good English paragraph, meaning there's a lot of fluff in here you don't need. So I'm gonna highlight what you need. So the top of a 3/16 inch acrylic testing box is covered with an unknown 1/2 inch insulation. This 1/2 inch is important. That's how thick the insulation is. This is a 1/2 inch, so that's how thick that insulation is around it. This 3/16 inch acrylic box means nothing to me. This acrylic's not insulating at all. The dimensions of the box are 10 inches by 10 inches on each side. And then the sides are wrapped with a control insulating material, so almost all the heat loss is through a 10 by 10 inch unknown insulating material. What this means, we are only worried about one of these sides of the box. I know you can't hardly see that, but this is all I'm worried about. I'm worried about the heat that's coming through here. And then it's just saying don't worry about the top of the box. So they're basically saying don't worry about that. Determine the thermal conductivity. So this is my unknown. For the insulating material, if the 25-watt bulb, that sounds important, is used to heat the box. And you can assume the only heat loss in the box occurs through the 10 by 10 test area. So here it tells you again, you're only concerned about one wall. And the bulb maintains the inside temperature is 10 degrees higher than the outside. So that whole paragraph, that's all what I need. Everything else is fluff. So my known values. Let's start easy. What's my temperature difference?
10.
Yep, 10 degrees Celsius. My rate of energy transfer is
25 watts.
perfect, 25 watts, because remember, I know that the unit for this guy is always in watts. Here's where it gets a little tricky. What's the area, Lizzie, with your hand up?
No.
Okay. What's the area of this 10 by 10 area?
0.06 meters squared.
So it tells me it's 10 inches by 10 inches, right?
Yes.
But we need to convert this to meters because in the US, we're the only ones that deal with inches. The rest of the world's in the metric world, so we have to convert over to metrics.
That was 0.06 meters squared.
So the area of one of these sides here is 0.06 meters squared. If you did not convert that and you said that was 100 meters squared, your answer is not going to be right, but you might have went through the steps right, and so you still learned something. But you all were the last to see this, so I think I caught most of you all to convert. B-Day was not so lucky. And then how thick is this guy? It's a 1/2 inch. Same thing, I gotta convert it over.
0.0167.
And so when I convert it, it's a 1/2 inch equals in meters, 0.0127 meters. So then my unknown value is K, which is thermal conductivity. Just in case there's any confusion. And so if I'm looking for K, which equation am I going to use?
K equals PL over A delta T.
Perfect. K equals PL over A, and then delta capital T, your temperature difference. And then you start plugging, and then you can solve for it. So K, you've done the hardest part, by the way. This is the hardest part. What we do today, I give you in metrics, and the quiz, I will already give it to you in metric. Oh, you won't have to convert anything. So what's P?
25.
25. And then the thickness is,
0.02.
y'all are amazing. And then the area,
0.06.
and then temperature difference.
10.
Perfect. Solve it down. Mason, what'd you get?
0.529 joules over SS.
Perfect. A roundish here, depending on how you round it, you could have gotten as low as 0.49, 0.53. I didn't tell you what to round to. On the quiz, I will make sure you know what to round to. Just in case, how we got this, like I can even break this down more. It ends up being 25 times this equals this, 0.06 times 10, and then that's how we got to this point. But we good? Help a little? Alright, so what's my U value? What is a U value? So the ability to conduct heat. Anybody remember what unit we use in the US? Y'all are awesome. Y'all are the first class that's gotten it. BTUs.
What does that actually stand for? What is the actual?
Big trunk underbelly.
That one. Big truck underbelly, I like that.
But what? What's the literal?
That is literal, baby. That's it.
Here, I'm actually gonna show you.
Big,
Oh, it's not hot.
big,
We're gonna get a load real quick.
big thermal unit. Basic time units. Basic thermal unit.
Basic thermal unit. Cool. I didn't know.
I didn't know that either. I just guessed.
No, you did know. Big truck underbelly.
Yeah.
So I'm gonna go look, and so I told you that's how they were measured. So only heaters will tell me a BCU, a BTU. Air conditioners won't, because ACs you don't want to really conduct heat. So I'm just gonna click on this random thing here. So this would get plugged into a living room or something.
I got 200.
5,200 BTUs. What about this guy?
No, I'm not. I guess that's like used for heat.
1,500. 5,120.
So 5,120 watts. If we continuously started clicking, we would start seeing a trend. This is pretty common for like an in-room heater. What type of heating is this?
Convection.
Correct. So there's liquid going through here, so that's what kind of heater that is. For fun, you can kind of see it already. So those normal ones you put in your living room, 5,000. This one's 60,000 BTUs. You would not put this in your living room though. You connect this to a propane heater, and it basically shoots fire out through this.
So don't put it in.
So put it in.
Yeah. Wait, can I angle it upwards so it's just like a.
We know that.
Okay, so I would like to define BTU. BTU stands for British Thermal Unit, and you see 1 BTU is the amount of energy needed to raise 1 pound of water at sea level.
Wait, why is it British man?
There you go. So this particular heater uses propane.
But it's also compared to.
I mean, it doesn't sound like a giant flame, but it's pretty. So the point of a heater like this, you're gonna use this more of like in a commercial setting, like a warehouse, like a garage that doesn't have insulation. this is definitely like a commercial type.
How big is it?
I have a friend who put this while he was building his shop and didn't have AC or heat or anything yet. He put this in there while they were working. Like big giant, like think those big garages that are like aluminum sided garages. There's no insulation on that aluminum. They're gonna use something like that in there.
It's not bad for a heavy water.
Oh no. They suck some propane though. So you think about to refill propane tanks, $20, like.
Yeah.
Alright, U value is the ability to conduct heat. What's the R value? The ability to. Y'all are awesome. So in here, we're gonna do R values with the side of houses. Alright, so I got this. I'm gonna start at 5H drywall and I'm gonna go clockwise around. So 5H drywall, I'll come here and I'm gonna look, oh, there it is, 5H drywall, come across, here's my R value. And it ends up being 0.56. I'm looking at 3.5 inches of fiberglass. I'm gonna go here, here's fiberglass, I come across, 3.142, is that my answer? No, I gotta times it by 3.5 because it was only per inch. There's some trickery there. So it's 10.997. You might have rounded to 11. 1 inch extruded poly. It's on here 2 different ways, and I'll show you. It's up here under extruded poly, and I come over to 4. There's also 1.5 poly here, but it's also down at the bottom of 4, and it's down here per inch. So if you had 3 inches of poly, extruded poly, which is unusual, you would find it down here. But it's the same, so 4. Wood bevel lap siding. Bless you. Bless you. Under siding, we have wood shingles, wood drop, but then we have wood bevel laps, and that's what we're looking for, 0.8. So don't let that get you confused there. And then the 2x4 and the floor, 2x4, 2x4, 4.38. So I got all my numbers now. I'm just going to do some addition. So the numbers for the wall value. It's like I drew a hole, took a drill and went through the side of my wall. I'm going to use this number. I'm going to use my fiberglass. I'm going to use the poly, and I'm going to use the wood siding. If I drill through the wall, I'm not going anywhere near that 2x4, so I don't need that. So you're going to add them together. 0.56, 10.997, 4, and then 0.8. Add them all up. 16.36, depending on how you round it. But that is my R value for the wall. And so now what I need to do is I need the R value at the stud location. So it's like you're going to drill a hole through the floor. And so you're going to drill through drywall. You're not going to go through any fiberglass, but you're going to go through some poly. You'll go through the wood siding, and you're going to go through the 2x4. And so those are the numbers now that you're going to add. So it's going to be 0.56 plus 4 plus 0.8 plus 4.38. You're going to add them up. 9.74, and you're done. Now, in this particular class, your wall cavities are going to be higher than your stud locations. Your walls are typically a lot better at insulating heat. So on the quiz next week, if your stud location is higher than your wall cavity, a red flag should go off in your head and you go, whoa, something's not right. And most likely you've added fiberglass in there and it's not in there.
Oh, so you don't have construction with a 2x4 for wall cavity R?
No. You do the 2x4s and the stud looking sheet.
So the stud's always lower than the cavity.
For this class, yes. I mean, there's sometimes in the real world it might not be like that, but for this class. You feel better?
No.
Yeah.
Oh. Might be a document stuffing. Alright, so let me go over the practice, what you're gonna spend the rest of the class on.